Alright, hello everybody and welcome to this week's video. This week we will be tackling something interesting. I haven't done much Feynman stuff, and he's quite a cool guy. So this week we're going to be looking at the exact path integral for a free particle. So we want to find this quantum mechanical propagator, K, for a free particle. So v of x is 0, and here we have that it's defined by the Feynman path integral over all possible trajectories x, of course the action, and then we have the weighting for each one. We can find our action for a classical particle. We say that S is between 2 times, so T1 and T2, of half mx dot dt. Of course, it's just the integral of the kinetic energy because the potential energy is 0. And here we have a total time t, which is T2 minus T1. What we want to do now is discretize the action. Discretize probably. Anyway, it's fairly, I don't want to say simple, but I think it's fairly simple. What we want to do is take our time interval t and slice it into n infinitesimal steps, and we have each step has a duration epsilon, which we'll call t over n, which is just, of course, the total time of the number of steps. It's going to be the length of each step. And we can define... we can define a discretized time, or just a discrete time, tj. Excuse me. That will be equal to ti plus j epsilon, and we have intermediate positions as well. X sub j equal to x of t sub j. And we ought to define some boundary conditions. So x naught is equal to xi, and xn is equal to xf, obviously, from our definition up there. So we can approximate the time derivative of our position function to be, I'm not going to go into this, but it ends up being x over xj plus 1 minus xj over epsilon, and hence we get a discretized sum as our action because we can plug that in, and we have a discrete number of steps now, n, so we say that s therefore is roughly equal to the infinite sum from j equals 0 to n minus 1 over half m, and then that squared, so xj plus 1. Oh my goodness, what's happening today? It's not particularly cold or anything. Times epsilon, which replaces our dt, and this is just the sum from j equals 0 to n minus 1 of m over 2 epsilon. Xj plus 1 minus xj squared. Nice. Yep. Yeah, that makes sense. Because we can expand our definition of the path integral. Measure dx. I can't do the cool one or whatever it is, so my usual d's look like that. My Feynman d's do that. They're kind of like Among Us things. So that's, yeah, that kind of thing. Anyway, we'll write out the definition. x being this limit as n approaches infinity, if I can write it, with a normalization factor of a to weight each path, and then I'll just write out, d of x1 times the next integral dx2 dot 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 all the way to the integral infinity to infinity of dx sub n minus 1, and that defines our entire sum here. And we can, well, the value for a is of course m over 2 pi I h bar c, no, epsilon or c, epsilon. Memory is failing me. So if we sub this discrete measure into the propagator, of course this is k, or it will be k, is this lim as n tends to infinity of a to the n, capital N, silly me, of all our integrals, plus the integral or times the integral of the exponent of that, which is this, I m over 2h bar epsilon from there, and the sum j equals 0, sorry, from there and there. Of xj plus 1 minus xj squared dx1 dot 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 dx, because obviously there's a lot of integrals there. Simplify that a bit. I'm gonna define a constant alpha to be m over 2I h bar epsilon. It's a bit weird, but we remember that I is equal to minus 1 over I. So thus the argument for this exponential, or rather I'm just going to take out the exponential part, it will become minus alpha xj plus 1 xj squared, and that just, or rather the integral of that dx1 just evaluates to or rather the normalization factor. A is just alpha over pi, yeah, because it simplifies up there. So we have successfully discretized the action, which is important. So continuing on, we end up with a number of Gaussians here, nested integrals. So we'll start with an identity, and that identity is the product of two Gaussians. I hope no one minds I'm using x instead of e to the whatever. X minus xa squared minus b. This is just two Gaussian products. Obviously if you expanded that, they would end up being products. Brilliant. In fact, we will expand it. So just the inside, minus a x squared plus 2x xa squared minus b x squared minus 2x xb plus xb squared. And this is equal to minus factoring out minus a plus, yeah, x squared plus 2ax a plus b x b x minus ax squared a plus b. Brill. Complete the square, I think, is what I would like to do. Yeah. Yeah. We can do something with this. Just the last two terms. A squared x squared sub a plus 2abx a x b plus b squared x squared b minus a plus b a x squared a plus b x squared b all over a plus b. That should simplify quite nicely, I think. A b x squared a plus b is equal to minus ab over a plus b. Factor that out is x a minus xb all squared, which is perfect square. And the integral of which yields pi over a plus b, I think he says. Yeah, so we get that integral from minus infinity to infinity, x minus a x minus x sub a. I'm going to write it again. Here I am writing it again. Nice. That is most certainly better. So, good identity. That is an identity, so I can put 3 there. Cool. I'm doing sneaky mathematician things, like writing 3 equal signs. Let's move on to evaluating the first time slice to get an idea. Yeah, because then I think we can use induction. So, I sub 1 is this integral. I'm not going to write it again. How do I get this stuff back? There we go. Gimme. I sub 1 is equal to that. Which is equal to, this should be x1, that should be x0, that should be x2, that should be x1. The x1, everything else is fine, so this yields pi over 2 alpha. I forgot this should be alpha. That should also be alpha because we got that earlier. exponent of minus alpha squared over 2 alpha x2 minus x naught squared, which is pi over 2 alpha. Obviously that cancels. Well, that's not really alpha, is it? That cancels. Exponent of minus alpha over 2 x sub 2 minus x 0. Interestingly, we don't have x1 in this expression, but the coefficient here is halved, so we just have a straight link between x1 and x2, plus that extra term of pi over 2 alpha. Yep. Now what we can do is iteration and some induction-y kind of things. So if we insert I1 back into our main expression and perform our integral over x2, we get this. Applying our identity from before, this is just pi over 3 alpha over 2 exponent of alpha squared over 2 over 3 alpha over 2. That cancels. X3 minus x naught squared, and this is just 2 pi over 3 alpha square root exponent of minus alpha. Nice, very cool. Now we start to see a pattern. I could do this again, but I'm not going to. It's kind of obvious, and I'm not a crazy maths person. That's my base case, and that's my case for K, if we want to be all induction-y about it. Anyway, n minus 1 is root of n minus 1 pi over n alpha exponent of minus alpha over n minus x naught squared. You could write this of I of n instead, but O n plus 1, n minus 1 is a bit easier. So in this case, n would be 3 for that one. Then clearly 3 minus 1 is 2, 3. Alpha over 3. Everything that makes sense. That should be xn though. Yeah, just 3. Okay. Now what we need to do is perform this n minus 1 times. And what we want to find is the total prefactor. And that ends up being actually not that hard to do. So this part 4 minus 1 would be pi over 2 alpha times 2 pi over 3 alpha times 3 pi over 4 alpha times ... all the way up to, let me put those in just to make it clear, root of n minus 1 pi over n alpha. And no, I'm not supposed to cancel those out. That cancels, that cancels, that cancels, blah, blah, blah. And then that would cancel. So it would just leave pi to the n minus 1 over n alpha to the n minus 1. Roots. Yes. This is good. This is what I wanted to see at the end of doing all of that. This is the bit that is in my notes, and that's correct. We are nearing the end. Shorter video, which is, I'm sure, a nice break. Anyway, final expression for k. And we need to multiply by the original normalization, which I nearly forgot. Yeah, that's fine. I forgot that whilst I was writing my notes and testing everything out, so I knew what I was doing. And it took me a very long time to work out what I'd done wrong. That times the exponent of minus alpha over n. Oh, why am I not talking? I'm sorry, I'm just concentrating deeply. Again, this is all just rearranging. That should be infinity, not alpha. Of root of alpha over pi n exponent of minus alpha over n x sub n minus x sub naught squared sub naught. Funny. And now we just throw in our definitions from before. We know that alpha over n is m over 2I h bar n epsilon, which is just t h bar t is minus I m over 2h bar t. I'm not sure why I keep doing my h's weird. And we can put this back in to get a final function for k. Thus k is equal to square root of m over 2 pi I h bar t exponent of I m, not imaginary, I, no, I want I at the beginning though, I m xf minus xi squared over 2 h bar t. Yay! Slap a box around it, and that is the free particle propagator. K. Okay. Haha, see what I did there? Okay. Yeah, that was quite an algebra heavy one. I don't know, I always feel that Feynman did a lot more maths. Or the stuff he did. Maybe he was just unlucky. Had to do all the completing the square and proof by induction. Like, I don't know, physicists wouldn't have noticed that. Although I guess this is coming out of a time where physicists and mathematicians and chemists, to be honest, are barely separated from each other. Regardless, I very much enjoyed doing that. It was a really fun one to read about and then realise. And I haven't done so much Feynman path integral formulation-y bits and bobs. I think I might go for a derivation-ish type thing. I wonder, what do I have planned? I was thinking of maybe a time slicing Schrodinger's equation derivation with the k propagator, because you can write k is also equal to you can write in bracket notation I times the Hamiltonian operator T over H bar, like that. But I don't know. We'll see. Anyway, in the meantime, I hope you enjoyed this video, and yeah, I'll see you next week. Goodbye.